Imagine two objects, each barely the size of a city, yet containing more mass than our entire sun, spiraling toward each other at a significant fraction of the speed of light. You might think the real story begins the moment they collide, but it doesn't. In the final minutes before these neutron stars ever make physical contact, something extraordinary is already happening in the space between them. Their magnetic fields, trillions of times stronger than anything ever produced on Earth, are reaching across the shrinking gap, connecting, twisting, snapping apart, and violently reconnecting. Enormous electrical currents begin surging through superheated plasma. Particles are being launched to nearly the speed of light. Energy is being released in ways we are only now beginning to understand through simulations. The collision hasn't started yet, but the war between their magnetic fields already has. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel out. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the objects themselves, because before you can understand what happens when two neutron stars' magnetic fields interact, you need to appreciate just how extraordinary a single neutron star actually is. Not just remarkable, not just unusual. A neutron star is one of the most extreme objects the universe has ever produced. It pushes the laws of physics to places that most people never think about. And once you understand what a neutron star is, once you really grasp the environment surrounding it, the events we're going to explore later will make a lot more sense. A neutron star begins its existence in violence. To understand how one forms, you have to go back to the life and death of a massive star. Throughout the universe, stars are born from collapsing clouds of hydrogen gas. Gravity pulls the gas together, compressing it until the core becomes hot enough and dense enough for nuclear fusion to ignite. Hydrogen atoms are crushed together, forming helium, and this process releases energy. That energy pushes outward, creating pressure that balances against gravity. As long as this balance holds, the star lives. For a star like our sun, this balance lasts about 10 billion years. Our sun is roughly halfway through its life. It's a relatively small, quiet star that will eventually swell into a red giant, shed its outer layers, and leave behind a dense remnant called a white dwarf. The sun's death will be dramatic by human standards, but peaceful by cosmic standards. No explosion, no catastrophe, just a slow, graceful fading. But stars much more massive than our sun follow a different path. Stars with 8 or more times the sun's mass burn through their fuel far more quickly. A star 20 times the mass of the sun might exhaust its hydrogen in just a few million years compared to the sun's 10 billion. And when a massive star begins running out of fuel, it doesn't go quietly. As the hydrogen in the core is used up, the star begins fusing heavier elements. Helium fuses into carbon, carbon fuses into neon, neon into oxygen, oxygen into silicon. Each stage produces less energy and lasts for a shorter time. The hydrogen burning stage lasted millions of years. The silicon burning stage lasts only about a single day. And then the star produces iron in its core. Iron is a dead end. Fusing iron doesn't release energy, it actually absorbs energy. So when the core fills with iron, the engine that has been keeping the star alive for millions of years suddenly shuts off. There is no more outward pressure to fight against gravity. And gravity has been waiting patiently for this moment for millions of years. What happens next takes less than a second. The iron core, which has accumulated a mass of roughly 1.5 times our Sun, collapses under its own gravity. It falls inward at speeds that can reach a quarter of the speed of light. In less than a second, a core that was roughly the size of Earth gets crushed down to a sphere about 12 miles across. 12 miles! That's roughly the distance from one end of a city to the other. All the mass of a star, compressed into something you could almost drive across in 20 minutes on a highway. The outer layers of the star, suddenly unsupported, come crashing inward too. But they slam into this incredibly dense core and bounce off, producing an enormous shockwave that tears the star apart from the inside out. This explosion is what we call a supernova. For a few weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. The energy released in that explosion is almost beyond comprehension. More energy is released in those few seconds of core collapse than our Sun will produce in its entire 10 billion year lifetime. And when the explosion clears, when the debris has been flung outward into space at thousands of kilometers per second, what's left behind at the center is a neutron star. A ball of matter so dense that the atoms themselves have been crushed out of existence. Under the unimaginable pressure of the collapse, electrons were forced into protons, converting them into neutrons. The entire core is now made almost entirely of neutrons, packed together so tightly that they're touching. There is essentially no empty space inside the neutron star. Every gap that normally exists between and within atoms has been squeezed out. The density is staggering. A single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. Think about that for a moment. A teaspoon. The amount of sugar you stir into your coffee. Except this teaspoon weighs 1 billion tons. If you could somehow bring a teaspoon of neutron star material to Earth's surface, it would be heavier than a mountain. It would sink through the ground, through the bedrock, through the mantle, all the way to the core of the planet, because nothing on Earth could support that weight. Nothing could even come close. The gravitational pull at the surface of a neutron star is about 200 billion times stronger than gravity on Earth. If you dropped an object from a height of 1 meter above the surface, it would hit the ground in about 1/1,000,000th of a second, traveling at roughly 7 million kilometers per hour at the moment of impact. The surface is a place of extremes that make every other environment in the known universe seem gentle. Now, here is where things get truly interesting for our story. Because a neutron star doesn't just have extreme density and extreme gravity, it also has one of the most powerful magnetic fields in the entire universe. To understand why, you need to know about a principle in physics called the conservation of magnetic flux. This principle says that when a conducting object shrinks, its magnetic field gets stronger. Not just a little stronger. The field strength increases in proportion to how much the surface area decreases. Think of it like this. The original star, before it collapsed, already had a magnetic field. Most stars do. Our Sun has a magnetic field. It's not particularly strong by cosmic standards, maybe a few Gauss on average, which is roughly comparable to a refrigerator magnet. The massive star that will become a neutron star also has a magnetic field, perhaps a few hundred or a few thousand Gauss across its enormous surface. But during the supernova, when that core collapses from something the size of Earth down to something 12 miles across, the surface area shrinks by a factor of several 100,000. flux conservation alone would amplify a field of a few thousand Gauss to roughly a billion Gauss. But the collapse is also violently turbulent, and convective motions in the collapsing material act as a dynamo, twisting and stretching the field, amplifying it further still. The combined effect produces a surface field of 1 trillion Gauss or more on the newborn neutron star. 1 trillion Gauss. Earth's magnetic field is about half a Gauss. A hospital MRI machine produces a field of maybe 30,000 Gauss. The strongest continuous magnetic fields ever produced in laboratories on Earth are about 450,000 Gauss. A neutron star's magnetic field is millions of times stronger than anything humans have ever created, and it forms in less than a second during the collapse. But the magnetic field isn't the only thing that intensifies during the collapse. The neutron star also spins incredibly fast. This happens for the same reason an ice skater spins faster when they pull their arms in close to their body. It's a principle called conservation of angular momentum. The original star was rotating slowly, maybe once every few weeks or months, the way our own sun rotates roughly once every 25 days. But when that enormous core collapses from thousands of miles across to just 12 miles across, all that slow rotation gets compressed into a tiny volume. The result is that the newborn neutron star can spin dozens of times per second. Some neutron stars, called millisecond pulsars, spin hundreds of times per second. The fastest known millisecond pulsar completes over 700 rotations every single second. That means a point on its equator is moving at a significant fraction of the speed of light. An object roughly 12 miles wide, containing more mass than the Sun, spinning 700 times per second. The physics at play here are almost absurd in their extremity. So now you have this object. It's 12 miles across. It weighs more than the Sun. It's spinning dozens or hundreds of times per second. And it has a magnetic field 1 trillion times stronger than anything on Earth. This combination of rapid rotation and an incredibly powerful magnetic field creates something very important for our story. It creates the neutron star's magnetosphere. Here's how that works. On a neutron star, the magnetic field axis and the spin axis are almost never perfectly aligned. They're tilted with respect to each other, sometimes by a few degrees, sometimes by a lot more. This misalignment is crucial because the neutron star is spinning, and because the magnetic field is tilted, the magnetic field rotates with the star. Imagine a lighthouse beam sweeping around as the lighthouse rotates. The neutron star's magnetic field sweeps through space in a similar way, except instead of a beam of light, it's a colossal magnetic structure rotating at tremendous speed. This rotating, tilted magnetic field does something remarkable. It generates enormous electric fields at the surface of the neutron star. The physics behind this is deeply connected to the relationship between electricity and magnetism. A changing or moving magnetic field creates an electric field. This is the same principle that allows electric generators to work here on Earth. A magnet spinning inside a coil of wire creates an electric current. On a neutron star, the spinning magnetic field creates electric fields that are almost inconceivably powerful. The voltages generated across the surface of a neutron star can reach 10 trillion volts or more. These electric fields are so strong that they can actually pull charged particles right off the surface of the neutron star. The crust of a neutron star is made of tightly packed atomic nuclei, mostly iron, arranged in a crystalline lattice so strong that it makes the hardest materials on Earth seem like wet tissue paper. But even this incredibly tough surface can't hold on to its particles against electric forces this strong. Electrons and ions are ripped from the crust and flung outward along the magnetic field lines. Once these particles are pulled off the surface, something else happens. The particles are accelerated to tremendous energies by the electric fields. As they streak along the curved magnetic field lines, they emit radiation, high-energy photons. Some of these photons are so energetic that when they interact with the intense magnetic field, they spontaneously convert into pairs of particles, an electron, and its antimatter counterpart, a positron. These new particles are themselves accelerated and emit more photons, which create more pairs, which emit more photons. It's a cascade, a chain reaction of particle creation that fills the space around the neutron star with a dense fog of electrons and positrons. This cloud of charged particles, trapped and organized by the magnetic field lines, streaming along those lines, flowing outward and sometimes back inward, this is the magnetosphere. It is not empty space around the neutron star. It is a structured, dynamic environment filled with incredibly energetic plasma that is completely controlled by the star's magnetic field. Think of the magnetosphere as a kind of magnetic fortress. The magnetic field lines extend outward from the neutron star's magnetic poles, curve through space, and loop back to the other pole, forming closed loops. Charged particles can move along these field lines, spiraling around them, but they can't easily cross them. The magnetic field acts like a cage, confining the plasma, guiding it, shaping it. The magnetosphere isn't just a static bubble of magnetic influence. It's a living, breathing, dynamic structure that co-rotates with the neutron star. The magnetic field lines near the star are forced to spin at the same rate as the star itself. Plasma trapped on those field lines gets dragged along for the ride, whipping around dozens of times per second. Close to the star, this works fine. But as you move farther out, those co-rotating field lines are being asked to move faster and faster because they have to sweep through larger and larger circles in the same amount of time. Eventually you reach a distance where the co-rotating field lines would need to move at the speed of light to keep up with the star's rotation. This boundary is called the light cylinder. It's not a physical object, it's a conceptual boundary. A cylindrical surface around the neutron star, defined by the distance at which co-rotation would demand light speed. Inside the light cylinder, the magnetic field lines are closed. They loop out from one pole and return to the other, and charged particles are trapped on these closed loops, co-rotating with the star. Outside the light cylinder, the field lines can't close anymore. They're forced open, and particles on those open field lines stream outward into space, carrying energy and angular momentum away from the star. This outflow of particles and energy from the open field lines is what powers the beams of radiation that make neutron stars detectable from Earth. And this is how we first discovered neutron stars, not by seeing them directly, which is almost impossible because they're so small, but by detecting the beams of radiation they produce. In 1967, a graduate student named Jocelyn Bell Burnell was working with a radio telescope in Cambridge, England. She was studying a completely different phenomenon, the twinkling of distant radio sources caused by the solar wind. But in her data, she noticed something peculiar. There was a source that was emitting incredibly regular radio pulses, one pulse every 1.337 seconds. with a precision that rivaled the best atomic clocks on Earth. The signal was so regular that the research team initially half-jokingly considered the possibility that it might be an artificial signal from an extraterrestrial civilization. They even gave it the informal nickname LGM1, standing for Little Green Men. But it wasn't aliens. It was a neutron star. What Bell-Burnell had discovered was a pulsar, a rapidly spinning neutron star whose magnetic axis is tilted relative to its spin axis, so that as the star rotates, its beams of radiation sweep across our line of sight like the beam of a lighthouse. Every time the beam sweeps past Earth, we detect a pulse of radio waves. The regularity of the pulses comes from the incredibly stable rotation of the neutron star. These objects are so dense and so massive that their rotation barely changes over thousands of years. Since Bell-Burnell's discovery, astronomers have found over 3,000 pulsars in our galaxy. Some pulse slowly, once every few seconds. Others pulse hundreds of times per second, revealing neutron stars spinning at almost unimaginable rates. Each one is a spinning magnetic powerhouse, broadcasting its presence across light years of space through beams of radiation generated by its rotating magnetosphere. The existence of pulsars gave us direct confirmation that neutron stars are real, and that they possess the extreme magnetic fields and rapid rotation that theory had predicted. Pulsars became cosmic laboratories, allowing scientists to study physics under conditions that can never be replicated on Earth. The extreme density, the intense gravity, the colossal magnetic fields, all of these can be probed through careful observation of pulsar signals. But not all neutron stars are ordinary pulsars. Some are far more extreme. And to fully appreciate the magnetic environments that come into play when two neutron stars approach each other, you need to know about magnetars. A magnetar is a neutron star with a magnetic field that goes beyond anything a normal pulsar possesses. While a typical neutron star might have a surface field of around 1 trillion Gauss, a magnetar can have a field of 1 quadrillion Gauss, or even higher. That's roughly 1,000 times stronger than a regular neutron star's field, and roughly 1 quadrillion times stronger than a refrigerator magnet. At these field strengths, physics starts behaving in deeply strange ways. The magnetic field of a magnetar is so intense that it distorts the shape of atoms. Normally, atoms are roughly spherical, but in a magnetar's field, atoms are squeezed into long, thin cylinders, aligned with the field lines. The field is so powerful that it affects the vacuum of empty space itself. In quantum physics, the vacuum isn't really empty. It's filled with the fleeting pairs of particles and antiparticles that pop into existence and vanish almost instantly. In a magnetar's field, these virtual particle pairs become polarized and aligned, giving the vacuum optical properties similar to a crystal. Light passing through this magnetized vacuum travels at slightly different speeds depending on its polarization. The vacuum near a magnetar is literally birefringent. It splits light into 2 rays, something that normally only happens inside certain crystals. Magnetars were first recognized as a distinct class of neutron star in the 1990s, though hints of their existence had appeared earlier. The most dramatic evidence came on December 27th, 2004, when a magnetar designated SGR 1806-20 produced a giant flare so powerful that it briefly outshone every star in the entire Milky Way galaxy combined. The blast of gamma rays reached Earth from roughly 50,000 light-years away, and was intense enough to measurably compress Earth's magnetic field, and ionized part of our upper atmosphere. A single event from a single neutron star, roughly 12 miles across, located on the other side of the galaxy, affecting the atmosphere of our planet. That is the kind of energy that magnetar-strength magnetic fields can unleash. Now, we've been talking about the magnetic environment around a single neutron star. Whether it's an ordinary pulsar with a field of 1 trillion Gauss or a magnetar with a field 1,000 times stronger, the basic picture is the same. A rapidly rotating, intensely magnetized object surrounded by a dynamic magnetosphere, filled with relativistic plasma. The magnetic field lines extend outward, structuring the surrounding space, trapping particles, and channeling energy. It's a magnetic fortress of almost unimaginable power. But here's the question that drives the rest of our story. Neutron stars don't always exist in isolation. Sometimes, 2 neutron stars orbit each other. They spiral around a common center, each one carrying its own magnetic fortress, each one broadcasting its own rotating magnetic field into the surrounding space, each one surrounded by its own magnetosphere, packed with charged particles moving at nearly the speed of light. And sometimes, these binary neutron stars are spiraling inward. They're losing energy to gravitational wave emission, slowly but relentlessly falling toward each other over millions of years, their orbits shrinking, their speeds climbing higher and higher. As the distance between them decreases, their magnetospheres grow closer and closer together. What happens when those 2 magnetic environments begin to overlap? When magnetic field lines from one neutron star reach across the narrowing gap and encounter the field lines from the other? When 2 of the most powerful magnetic structures in the universe start to interact in the cramped space between 2 objects that are hurtling toward each other at a significant fraction of the speed of light? That question is what we're going to explore next. Because the answer, as recent simulations from NASA and research groups around the world have revealed, is far more violent, far more dynamic, and far more energetic than most people ever imagined. The collision between 2 neutron stars is one of the most powerful events in the cosmos. But the electromagnetic battle between their magnetic fields, the war that begins before the stars ever physically touch, that is a story in its own right. And it is only now beginning to be understood. So how do 2 neutron stars end up spiraling toward each other in the first place? It doesn't happen by accident. It requires a very specific sequence of events, each one improbable on its own, stretching back millions of years before the final collision ever takes place. It starts with 2 massive stars. Not just any stars, both of them need to be big, at least 8 times the mass of our Sun each. And they need to be born together, orbiting one another in what astronomers call a binary system. Binary star systems are actually quite common. Roughly half of the stars in our galaxy exist in pairs or larger groups, gravitationally bound to one another, orbiting a shared center of mass. So having 2 massive stars in a binary isn't unusual by itself. What makes this story unusual is what has to happen next, and the fact that the system has to survive it. The more massive of the 2 stars burns through its fuel first. Remember from our earlier discussion that the more massive a star is, the faster it consumes its nuclear fuel. So the heavier star in the pair runs out of fuel while its companion is still burning happily. The heavier star's core collapses. The outer layers explode in a supernova. And if the core is massive enough, a neutron star is left behind. But here's the problem. A supernova explosion is not gentle. It releases an enormous amount of energy, and it also delivers a powerful kick to the newborn neutron star. Depending on asymmetries in the explosion, the neutron star can be launched in a particular direction at hundreds of kilometers per second. This kick can easily disrupt the binary system. If the kick is too strong or aimed in the wrong direction, the neutron star goes flying off into space, leaving its companion behind. The binary is destroyed. And this is actually what happens in most cases. The majority of binary systems don't survive the first supernova, but sometimes the system holds together. Maybe the kick was relatively small, maybe the orbital parameters were just right. Whatever the reason, the surviving system now contains a neutron star orbiting a massive normal star. Time passes. The second star ages. It expands. It burns through its fuel. And eventually it too reaches the end of its life. Its core collapses. Its outer layers explode in a second supernova. And once again, the system faces the possibility of being torn apart by the violence of the explosion. If the system survives both supernova events, and the second collapse also produces a neutron star rather than a black hole, then you have something extraordinary. Two neutron stars orbiting each other, each one only about 12 miles across, each one more massive than the Sun, each one carrying a magnetic field trillions of times stronger than Earth's, each one spinning rapidly, each one surrounded by its own magnetosphere, filled with relativistic plasma. Two magnetic fortresses locked in a gravitational dance. These binary neutron star systems are rare. The double survival requirement means that only a tiny fraction of binary star systems produce them. Astronomers estimate that there are probably only a few tens of thousands of binary neutron star systems in our entire galaxy at any given time, out of hundreds of billions of stars. Finding them is difficult because both objects are small and faint. You essentially need at least one of them to be an active pulsar, broadcasting radio pulses that we can detect, in order to discover the system. Now comes the crucial part. These two neutron stars are not going to orbit each other forever. Something is slowly, relentlessly pulling them together. And that something is one of the most profound predictions of Albert Einstein's general theory of relativity. In 1915, Einstein published his general theory of relativity, a revolutionary framework that replaced Newton's understanding of gravity. In Einstein's picture, gravity isn't a force pulling objects together across empty space. Instead, massive objects warp the fabric of space-time itself, and other objects follow the curves in that warped space-time. Earth doesn't orbit the Sun because the Sun is pulling on it with an invisible rope. Earth orbits the Sun because the Sun's mass has curved the space-time around it, and Earth is following the straightest possible path through that curved geometry. One of the predictions of general relativity is that accelerating masses should produce ripples in the fabric of space-time. These ripples are called gravitational waves. They propagate outward at the speed of light, stretching and compressing space as they pass. Any system with accelerating masses produces gravitational waves, but in most everyday situations the waves are unimaginably faint. The gravitational waves produced by a person waving their arms, for example, carry so little energy that they could never be detected by any conceivable instrument. But binary neutron stars are not everyday objects. Two objects, each more massive than the Sun, orbiting each other at high speed, constantly accelerating, constantly changing direction. This system produces gravitational waves that, while still extraordinarily faint, by the time they reach Earth, carry significant energy away from the binary. And this is the key point. The gravitational waves carry energy. That energy has to come from somewhere. It comes from the orbital energy of the binary system itself. As gravitational waves carry energy away, the orbit loses energy. And when an orbit loses energy, it shrinks. The two neutron stars move slightly closer together. Their orbital period gets slightly shorter. They move slightly faster. And because they're now closer and moving faster, they radiate gravitational waves even more strongly, which causes them to lose energy even faster, which makes the orbit shrink even more. It's a positive feedback loop. A slow spiral inward that accelerates over time. The first observational proof that this actually happens came in 1974, when two American astronomers, Russell Hulse and Joseph Taylor, discovered a remarkable system using the Arecibo radio telescope in Puerto Rico. They found a pulsar, designated PSRB 1913+16, orbiting another neutron star. Because one of the neutron stars was a pulsar, sending out regular radio pulses like a cosmic clock, Hulse and Taylor could track the orbit with extraordinary precision. They measured the orbital period down to fractions of a millisecond, and then watched how it changed over the following years. What they found was stunning. The orbital period was decreasing. The two neutron stars were spiraling inward, and the rate at which the period was decreasing matched the predictions of general relativity for gravitational wave emission to within a fraction of a percent. It was beautiful, elegant, undeniable proof that gravitational waves are real and that they carry energy away from orbiting systems, exactly as Einstein had predicted 60 years earlier. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. Their binary pulsar remains one of the most important confirmations of general relativity ever achieved. It showed that gravitational waves aren't just a theoretical curiosity. They have measurable, observable consequences. They drain energy from orbiting systems. They cause orbits to decay. And given enough time, they will cause the two orbiting objects to collide. But how much time does this process take? The answer depends on how close the neutron stars start and how massive they are. For the Hulse-Taylor binary, the current orbital period is about 7 hours and 45 minutes, and the orbital decay rate predicts that the two neutron stars will merge in roughly 300 million years from now. That might seem like a long time, and it is by human standards, but by cosmic standards, it's not that long at all. The universe is nearly 14 billion years old. 300 million years is only about 2% of the universe's age. Other binary neutron star systems are much closer to merging. Some have orbital periods of just a few hours. Some are predicted to merge within tens of millions of years. And somewhere in the universe right now, at this very moment, binary neutron stars are in their final minutes before collision. The gravitational waves they're emitting are washing over us right now. Too faint for our current detectors to pick up from most of the universe, but real and present nonetheless. Let's talk about what those final minutes look like. Because the inspiral doesn't proceed at a constant rate. It accelerates dramatically. For most of the binary's life, the orbital decay is glacially slow. Over millions of years, the orbital period shortens by tiny fractions of a second. The neutron stars edge closer together so gradually that you'd never notice even if you could somehow watch the system for a human lifetime. But as the orbit shrinks, the gravitational wave emission gets stronger. The system radiates more energy. The orbit decays faster. The neutron stars spiral inward more quickly. And this acceleration itself accelerates. Think of it like water swirling down a drain. Far from the drain, the water moves slowly, but as it spirals closer to the center, it speeds up. And the closer it gets, the faster it goes. Until at the very end, it's whipping around at tremendous speed before plunging down the hole. The neutron star inspiral follows a similar pattern. Millions of years of slow approach, thousands of years of noticeable acceleration, months of rapid inspiral, minutes of furious orbiting, and finally seconds of ultra-relativistic spiraling before the stars make physical contact. In the final 10 minutes or so before merger, the two neutron stars might be separated by a few hundred kilometers, which sounds like a lot until you remember that these are objects more massive than the Sun. They're orbiting each other several times per second at this point. Their orbital velocities have climbed to a substantial fraction of the speed of light, perhaps 10 to 20%. The gravitational waves they're producing are now enormously powerful, carrying away energy at an incredible rate, causing the orbit to decay visibly on a timescale of minutes. In the final seconds, the orbit shrinks to just a few tens of kilometers. The neutron stars are now orbiting each other hundreds of times per second. The gravitational wave frequency has climbed from a few hertz to over 1,000 hertz. The gravitational wave signal, which astronomers call the chirp, sweeps upward in both frequency and amplitude, getting louder and higher pitched as the stars spiral closer, faster and faster, until the signal cuts off at the moment of contact. Now. Here is where our magnetic story truly begins. Because throughout this entire inspiral, we have not just two gravitational objects spiraling toward each other. We have two magnetized objects, two neutron stars, each wrapped in its own magnetic fortress, each surrounded by its own dynamic magnetosphere packed with relativistic plasma. And as the orbital separation shrinks from hundreds of kilometers to tens of kilometers to mere kilometers, those magnetospheres inevitably begin to encounter each other. At large separations, when the neutron stars are hundreds or thousands of kilometers apart, their magnetospheres don't interact much. Each magnetosphere occupies the space immediately around its neutron star, and the gap between them is large enough that the magnetic influence of one star is negligible at the location of the other. They're like two magnets on opposite sides of a room. Each one creates a field in its immediate vicinity, but they're too far apart to feel each other's influence. But magnetic fields don't simply stop at some sharp boundary. They diminish with distance, but they never truly reach zero. As the orbital separation shrinks, the magnetic field from one neutron star at the location of the other neutron star grows stronger. At some point, the field from the approaching star becomes comparable in strength to the local field of the other star. And that's when things start to change, when the two magnetospheres begin to overlap. The magnetic field in the space between the stars is no longer dominated by just one star. It's a combination of both. And how those two fields combine depends critically on something that might sound technical, but is actually quite intuitive. It depends on the orientation of the two magnetic fields relative to each other. Every neutron star's magnetic field has a direction, just like a bar magnet has a north pole and a south pole. The magnetic field lines emerge from one magnetic pole, arc through space, and re-enter at the other magnetic pole. When two neutron stars approach each other, the relative orientation of their magnetic poles determines what happens when their fields meet. Consider the simplest case. Two bar magnets approaching each other. If you bring the north pole of one magnet toward the south pole of another, the field lines connect. They flow from the north pole of the first magnet, across the gap, and into the south pole of the second magnet, forming a smooth, continuous magnetic circuit. The magnets attract each other. The field in the gap is strong and well ordered. But if you bring two north poles together or two south poles together, the field lines collide head-on. They point in opposite directions across the gap. The fields don't connect smoothly. Instead, they press against each other, creating a region of intense stress where oppositely directed field lines are forced close together. The magnets repel each other. Something very similar happens with neutron star magnetospheres, though the reality is far more complex because the fields are rotating, the stars are moving, the geometry is three-dimensional, and everything is bathed in relativistic plasma. But the basic principle holds. The relative orientation of the magnetic dipoles matters enormously. When the magnetic fields are anti-aligned, meaning the north pole of one star's field faces the north pole of the other, or equivalently, the field lines point in opposite directions across the gap, the fields can't smoothly connect. Instead, they press against each other, creating a thin boundary layer where oppositely directed field lines are compressed together. This configuration stores enormous amounts of magnetic energy in that boundary layer, like a spring being compressed. And this stored energy will eventually be released explosively, through a process we'll discuss shortly. When the fields are aligned, meaning the field lines from one star run in roughly the same direction as the field lines from the other at the point where they meet, the situation is different. The fields can merge more smoothly. Field lines from one star can connect to field lines from the other, forming magnetic bridges that span the gap between the two neutron stars. These connections create what physicists call magnetic flux tubes, bundles of connected field lines that stretch from one star to the other, like ropes tying them together. In reality, the situation is never purely aligned or purely anti-aligned. The magnetic dipoles of the two neutron stars are tilted at various angles relative to each other and relative to the orbital plane. The stars are spinning, so the dipole orientations are constantly changing. As the stars orbit, the geometry shifts with every revolution. At some points in the orbit, the fields might be roughly anti-aligned, pressing against each other. A fraction of a second later, as the stars have moved and rotated, the fields might be roughly aligned, allowing connections to form. The magnetic interaction is not constant. It flickers and oscillates, switching character with every orbit, every rotation, every shift in geometry. But regardless of the specific orientation at any given instant, one thing is certain. As the separation decreases, the interaction between the two magnetospheres intensifies. The magnetic fields in the space between the stars grow stronger. The forces acting on the plasma in that region grow more violent, and the amount of magnetic energy stored in the interaction region grows dramatically. Let's pause here and talk about what happens to the space between the stars, because this transformation is extraordinary in its own right. At large separations, the gap between the neutron stars is essentially empty. Not perfectly empty, because interstellar space always contains a thin scattering of particles, perhaps a few atoms per cubic centimeter. But compared to the dense magnetospheric plasma surrounding each neutron star, the gap is a void. There's nothing there, just darkness and distance. As the magnetospheres begin to overlap, that changes. The first thing that happens is that the magnetic fields from the two stars begin to fill the gap with their influence. Magnetic field lines from one star thread through the region where the other star's field is also present. The gap is no longer magnetically empty. It's permeated by overlapping fields from both stars, creating a complex, combined magnetic geometry that changes with every orbit. Once those overlapping fields are present, the gap begins to fill with plasma. This happens through several mechanisms. Particles that were previously trapped on closed magnetic field lines near one star find themselves on field lines that now extend across to the other star. These particles can slide along the shared field lines and stream into the gap. It's like opening a gate between two enclosed pastures. The particles were confined before, but now there's a path connecting the two environments, and the particles flow through it. Additionally, the intense and rapidly changing magnetic fields in the gap generate electric fields. These electric fields can accelerate any stray particles that happen to be in the region, boosting them to high energies. And high energy particles moving through strong magnetic fields radiate photons. Some of those photons are energetic enough to interact with the magnetic field and produce electron-positron pairs. Those new pairs are themselves accelerated, producing more photons, creating more pairs, in a cascade that we encountered earlier when discussing individual magnetospheres. The same cascade process that fills the space around a single neutron star now operates in the gap between two of them, generating fresh plasma from pure electromagnetic energy. The result is that over the final minutes and seconds of inspiral, the gap between the neutron stars transforms. It goes from being an empty void to being a dense, hot, electrically active medium. The plasma in the gap is not ordinary gas. It's a relativistic plasma, meaning the particles are moving at speeds close to the speed of light. It's a magnetized plasma, threaded through with powerful magnetic fields from both stars. It's a pair plasma, composed primarily of electrons and positrons, rather than the protons and electrons that make up ordinary matter. And it's an electrically active plasma, carrying enormous currents along the magnetic field lines that connect the two stars. This transformation matters because the plasma in the gap doesn't just sit there passively. It participates actively in the magnetic interaction. The plasma carries currents that modify the magnetic field geometry. It responds to electric and magnetic forces by moving, flowing, swirling through the gap in patterns dictated by the combined fields of both stars. It mediates the connection between the two magnetospheres, acting as the conducting medium through which electrical energy flows from one star to the other. Without this plasma, the magnetic interaction would be very different. The plasma makes everything more intense, more dynamic, and more capable of producing the violent energy releases that we'll discuss shortly. Now let's talk about what happens when field lines do connect between the two stars. When a magnetic field line from one neutron star links up with a field line from the other, it creates a shared magnetic structure that spans the gap. Charged particles, electrons, positrons, and ions can now flow along this connected field line from one magnetosphere to the other. The two previously independent magnetic environments are now electrically connected. This has profound consequences. Enormous electrical currents begin to flow along the connected field lines. These aren't ordinary currents like the ones in your household wiring. These are relativistic currents, streams of charged particles moving at nearly the speed of light, carrying enormous amounts of energy from one magnetosphere to the other. The connected field lines act like superconducting wires linking two colossal magnetic generators, and the currents that flow through them are staggering. Think about what this means in terms of energy. Each neutron star is a spinning magnetic object, and a spinning magnet is fundamentally an electrical generator. The rotating magnetic field of a neutron star generates voltages of trillions of volts. When the two magnetospheres connect, it's as if you've wired together two generators, each producing trillions of volts through a conducting circuit made of relativistic plasma. The power flowing through those connected field lines is immense, far beyond anything that exists in any other astrophysical context, short of the merger itself. The space between the two neutron stars, which was previously near vacuum, has now become something utterly different. It's become one of the most electromagnetically active environments in the universe. A region threaded with powerful magnetic fields, filled with relativistic pair plasma, carrying colossal electrical currents, and crackling with energy being exchanged between two of the most extreme objects nature has ever produced. Now, here is where the orbital dynamics make everything worse, because the two neutron stars are not sitting still, they're orbiting each other. And as the inspiral progresses, they're orbiting faster and faster. Consider what happens to the magnetic connections between the stars during each orbit. At one point in the orbit, field lines connect between the two stars, forming flux tubes that span the gap. But then, the stars continue moving. They swing around each other. And as they do, those connected field lines get dragged along. The field lines can't simply snap into a new configuration instantaneously. They're anchored to the plasma and to the stellar surfaces. So as the stars orbit, the connected field lines get stretched, twisted, and wound up. Think of it like two poles stuck in the ground with a rope tied between them. If you start rotating one pole, the rope begins to wind around it. The rope gets tighter and tighter, storing more and more tension with every rotation. Something similar happens with the magnetic flux tubes between the orbiting neutron stars. Each orbit wraps the connected field lines tighter, adding more stress, storing more magnetic energy in the twisted configuration. But unlike a rope, magnetic field lines don't just keep twisting forever. There is a limit. As the stress in the twisted field lines increases, the magnetic configuration becomes unstable. The field lines are being forced into arrangements that store enormous amounts of energy, and the system wants to release that energy. It wants to rearrange itself into a lower energy configuration, and the orbital frequency is climbing. In the final minutes before merger, the neutron stars orbit each other several times per second. In the final seconds, they orbit hundreds of times per second. Each orbit adds another twist to the connected field lines. The rate at which magnetic stress accumulates increases dramatically as the inspiral progresses. The system is being wound up like a spring, tighter and tighter, faster and faster, with each orbit pumping more energy into the increasingly stressed magnetic field configuration. At the same time, the orbital velocity is climbing toward a significant fraction of the speed of light. This means the plasma between the stars is being stirred at relativistic speeds. Magnetohydrodynamic instabilities develop. The boundary layers between the two magnetospheres become turbulent. Waves propagate through the magnetized plasma. The entire interaction region becomes increasingly chaotic and violent. There's another effect that makes this even more extreme. As the neutron stars spiral closer together, the tidal forces between them grow enormously. Each neutron star's gravity distorts the shape of the other, stretching it slightly toward its companion. These tidal distortions affect the magnetic field geometry because the field is anchored to the stellar surface. As the surface deforms, the magnetic field footprints shift and the external field configuration changes. The magnetic interaction isn't just responding to orbital motion, it's also responding to tidal deformation, adding yet another layer of complexity and another source of variability. The system at this stage is extraordinary. Two objects more massive than the Sun, each 12 miles across, orbiting each other dozens or hundreds of times per second at a sizable fraction of the speed of light, separated by distances comparable to their own diameters. Their magnetic fields, trillions of times stronger than Earth's field, are reaching across the narrowing gap, connecting, winding up, storing enormous amounts of energy. Colossal electrical currents are flowing through the relativistic plasma that fills the space between them. The magnetic field configuration is being stressed to the breaking point with every orbit, faster and faster as the inspiral accelerates. And the stars haven't touched yet. They haven't made physical contact. The surfaces are still separated by the seething, magnetized, current-carrying plasma that now fills the gap between them. The gravitational wave signal is screaming upward in frequency and amplitude. The magnetic interaction is becoming more and more intense with every passing millisecond. Something has to give. Those stressed, twisted, wound-up magnetic field lines can't hold their energy forever. The magnetic configuration is becoming more and more unstable. At some point, the stress exceeds what the field can sustain, and the field lines break. But they don't just break and disappear. Magnetic field lines don't work that way. When they break, they reconnect in a new configuration, releasing the enormous energy that was stored in the stressed arrangement. This process, magnetic reconnection, is one of the most violent energy release mechanisms in all of astrophysics. It's the same process that drives solar flares on our own sun, but in the environment between merging neutron stars, it operates at energy scales that dwarf anything the sun has ever produced. What magnetic reconnection actually is, how it works physically, what it does to the particles and fields in the space between the stars, and why it might produce detectable signals that arrive at Earth before the collision itself, that is where we're heading next. Because reconnection is the engine that converts the magnetic energy stored in those stressed, tangled field lines into the raw violence that makes the pre-merger environment one of the most extreme electromagnetic laboratories the universe has ever created. So let's talk about magnetic reconnection, because this process is the engine that drives the pre-merger violence. It's the mechanism that converts all that stored magnetic energy, all that tension and stress built up in the tangled, twisted field lines between the two approaching neutron stars, into raw, explosive power. Reconnection is what turns the quiet accumulation of magnetic stress into particle acceleration, radiation, and possibly detectable signals that escape the system before the collision itself. But magnetic reconnection is one of those terms that gets thrown around in science documentaries without ever really being explained. You hear it during discussions of solar flares, you hear it when people talk about space weather, and now you're hearing it in the context of merging neutron stars. But what does it actually mean physically? What is happening to the magnetic field lines, to the plasma, to the particles when reconnection occurs? Let's break it down properly. Because once you understand this process, the rest of the story falls into place. Start with a simple picture. Imagine two regions of magnetic field pressing against each other, with the field lines pointing in opposite directions across the boundary between them. On one side, the field lines point to the left. On the other side, they point to the right. Right at the boundary, you have a thin layer where the field direction reverses. This is called a current sheet because the abrupt change in field direction requires an electrical current flowing through that thin layer to sustain it, according to the laws of electromagnetism. Now, magnetic field lines carry energy. The stronger the field and the more stressed its configuration, the more energy is stored. When you have two regions of opposing field pressed tightly together, there's an enormous amount of energy locked up in that configuration. The system is in a high energy state. Nature, as a general rule, prefers low energy states. The system wants to rearrange itself to release that stored energy, but it can't. At least not easily. Because in an ideal plasma, magnetic field lines are frozen into the plasma. They move with the plasma, and the plasma moves with them. The field lines can't just jump from one configuration to another. They're trapped. This is the bottleneck. The energy is there. The system wants to release it. But the frozen-in condition prevents the field lines from simply snapping into a new arrangement. The current sheet sits there, thin and stable, holding enormous amounts of energy in check, like a dam holding back a reservoir. But the frozen-in condition isn't perfect. In the real universe, plasma has finite electrical resistance, even if that resistance is extraordinarily small. And right at the center of the current sheet, where the field is weakest and the current density is highest, that tiny bit of resistance allows the frozen-in condition to break down in a very small region. The field lines, which were previously trapped and unable to cross the current sheet, can suddenly break and reconnect with field lines from the other side. What happens next is dramatic. Consider two field lines, one from each side of the current sheet, approaching the reconnection point. They're pointing in opposite directions. At the reconnection point, they break, and then the broken ends from opposite sides join together, forming two new field lines. Each new field line is sharply bent at the point where the reconnection occurred, like a rubber band that has been pulled taut and then released at the center. And just like a released rubber band, these newly reconnected field lines snap outward with tremendous force. They're driven by magnetic tension, the same force that makes a plucked guitar string spring back. The bent field lines straighten out, and as they do, they fling the plasma attached to them outward at enormous speed. The magnetic energy that was stored in the stressed configuration is converted into kinetic energy of the outflowing plasma and into heat. Particles that were sitting in the current sheet are suddenly blasted outward at speeds that can approach the speed of light. This is magnetic reconnection in its essence. Oppositely directed field lines are brought together. They break at a small reconnection point. They reconnect into a new configuration that has less magnetic energy. The difference in energy goes into accelerating particles and heating plasma. It is a way of violently converting magnetic energy into kinetic energy, thermal energy, and radiation. On the Sun, magnetic reconnection drives solar flares. The Sun's magnetic field gets twisted and stressed by the motions of plasma in the solar atmosphere. When stressed field lines are forced together and reconnect, the result is a solar flare, a sudden explosive release of energy that heats plasma to tens of millions of degrees and accelerates particles to high energies. The largest solar flares release energy equivalent to billions of hydrogen bombs detonating simultaneously. And yet, even the most powerful solar flare is a firecracker compared to what happens between merging neutron stars. Now, let me be more precise about the physics, because in the environment between two neutron stars approaching merger, reconnection doesn't work exactly the way it does on the Sun. There are crucial differences that make the neutron star case far more extreme. The first difference is the field strength. On the Sun, magnetic fields in active regions might reach a few thousand Gauss. Between merging neutron stars, the magnetic fields can reach trillions of Gauss. The energy stored per unit volume of magnetic field scales as the square of the field strength. So a field that is 1 billion times stronger stores a quintillion times more energy per unit volume. The amount of energy available for release through reconnection between neutron stars is almost incomprehensibly larger than anything the Sun can produce. The second difference is the plasma environment. On the Sun, the plasma is made of ordinary protons and electrons moving at speeds that are fast by human standards, but slow compared to the speed of light. Between merging neutron stars, the plasma is relativistic. The electrons and positrons filling the magnetosphere are moving at nearly the speed of light. This changes the physics of reconnection fundamentally. In relativistic plasma, the magnetic energy density can vastly exceed the rest mass energy density of the particles. This means that when reconnection releases magnetic energy, there is far more energy available than the particles need to reach extreme speeds. The particles can be accelerated to tremendous energies, far beyond what's possible in ordinary solar reconnection. The third difference is the geometry and timescale. On the Sun, reconnection events happen in specific active regions, and they last anywhere from minutes to hours. Between merging neutron stars, reconnection is happening everywhere in the interaction region between the two magnetospheres, and it's being driven by the relentless orbital motion of the stars themselves. Every orbit winds the connected field lines tighter, building up more stress, forcing more oppositely directed field lines together, triggering more reconnection. And in the final seconds before merger, the stars are orbiting hundreds of times per second. Reconnection is happening continuously, driven at a frantic pace by the orbital dynamics. Let me walk through what a single reconnection cycle looks like between two merging neutron stars. At some point during an orbit, magnetic field lines from the two stars connect across the gap. These connected field lines get dragged by the orbital motion, stretched and twisted as the stars continue to circle each other. With each orbit, the field lines accumulate more stress. The magnetic energy stored in the twisted configuration increases. Eventually, the stress exceeds a critical threshold. The field configuration becomes unstable. In the thin current sheets that form where oppositely directed field lines are pressed together, reconnection initiates. The field lines break and reconnect into a new, lower energy arrangement. The released energy goes into accelerating the plasma outward from the reconnection sites, heating the particles to extreme temperatures and launching jets of relativistic plasma along the newly reconnected field lines. But the story doesn't end there. The orbital motion continues. New field lines from the two stars are brought together. New connections form. New stress accumulates. And within a fraction of a second, another reconnection event is triggered. Then another. And another. The process is cyclical, but not periodic. It's chaotic, driven by the ever-changing geometry of the spinning, orbiting, tidally deforming neutron stars. Reconnection events fire at irregular intervals, producing bursts of energy that vary in intensity and location as the overall configuration shifts. With each orbit, the system gets wound up tighter, and with each reconnection event, some of that wound up energy is released. But the orbital motion keeps adding energy faster than reconnection can release it. The total magnetic energy in the interaction region climbs higher and higher as the inspiral progresses. Reconnection events become more frequent, more violent, more energetic. The system is escalating, feeding on itself, driven inexorably toward the final moment of contact. Now, let's talk about what happens to the particles, because this is where the story connects to things we might actually be able to detect. When reconnection occurs, particles in the current sheet are accelerated to extreme energies. In the relativistic environment between neutron stars, the accelerating electric fields can be enormous. Particles, mostly electrons and positrons, can be boosted to energies measured in mega-electron volts or even giga-electron volts. These are the same energy scales that particle accelerators on Earth achieve. But here the acceleration is happening naturally, driven by magnetic field reconfiguration in the most extreme electromagnetic environment the universe can produce. Once these particles reach high energies, they radiate. They have to. A charged particle moving at nearly the speed of light through a strong magnetic field emits radiation through a process called synchrotron emission. The particle spirals around the magnetic field line, and each time it curves, it emits a burst of electromagnetic radiation. The faster the particle is moving and the stronger the magnetic field, the more energetic the radiation. In the environment between merging neutron stars, synchrotron radiation from reconnection accelerated particles can produce photons across a wide range of energies. Some of the radiation comes out as radio waves, some as visible light, but the most interesting radiation from a detection standpoint comes out at much higher energies, X-rays and gamma rays. There is also another radiation process at work called curvature radiation. When charged particles are forced to follow curved magnetic field lines, they emit radiation in the direction they're moving. The tighter the curve and the faster the particle, the higher the energy of the emitted photons. In the intensely curved magnetic field geometry near the neutron stars, curvature radiation can produce extremely energetic photons, reaching into the gamma ray band. So reconnection accelerates particles. Those particles emit high energy radiation. And in principle, some of that radiation should be able to escape the system and travel outward into space, potentially reaching detectors on or near Earth. This is the basis for what scientists call precursor emission, electromagnetic signals that are produced before the neutron stars actually collide, generated by the magnetic interaction in the final moments of inspiral. But there's a complication, a big one, and this complication is one of the most fascinating aspects of the entire process. Not all of the high-energy radiation actually escapes. In fact, some of the most energetic photons produced by reconnection may never leave the immediate vicinity of the merging neutron stars. They can be destroyed before they get out. Here's why. When a very high-energy gamma-ray photon travels through an environment with an intense magnetic field, it can interact with that field in a remarkable way. If the photon energy exceeds a certain threshold, and the magnetic field is strong enough, the photon can spontaneously convert into a pair of particles, an electron and a positron. The photon disappears. In its place, two new particles materialize out of what was essentially pure energy being converted into mass. This is pair production, one of the most striking predictions of quantum electrodynamics, confirmed experimentally many decades ago. In the intense magnetic field environment between merging neutron stars, pair production can be extremely efficient. The magnetic field is so strong that photons with energies of just a few mega electron volts can undergo this conversion. And the reconnection process is producing plenty of photons at these energies and above. So what happens is a kind of self-limiting cycle. Reconnection accelerates particles. Those particles radiate high-energy photons. Some of those photons travel through the intense magnetic field and convert into electron-positron pairs before they can escape. Those new pairs are themselves accelerated by the fields, and they radiate more photons, some of which also convert into pairs. The result is that the space between the merging neutron stars becomes increasingly opaque to the highest energy photons. The very process that produces these photons also produces the conditions that prevent them from escaping. It's as if the system is trying to broadcast its violence to the universe, but keeps trapping its own signal. This doesn't mean nothing escapes. Lower energy photons in the X-ray band or even the ultraviolet are less susceptible to magnetic pair production. They can navigate through the intense field environment and leak out. And some higher energy photons produced in regions where the field is slightly weaker or oriented favorably might also escape. The system is not perfectly opaque. It's selectively opaque, blocking the most energetic radiation while allowing some lower energy radiation to leak through. Additionally, the conversion of photons into pairs doesn't destroy the energy. It just changes its form. The energy goes into the kinetic energy and rest mass of the new electron-positron pairs, which then radiate at low energies, producing photons that can escape. So the overall luminosity of the system might not be reduced much by pair production, but the spectrum, the distribution of energy across different wavelengths, is modified. The highest energy end gets suppressed. The energy comes out at lower frequencies instead. This is important for observers trying to detect precursor emission, because it means the signal might not appear where the most naive calculations would predict. It might show up at X-ray energies rather than gamma-ray energies, or it might appear as a complicated, rapidly varying mix of different wavelengths. Recent simulations have begun to reveal just how complex and dynamic this entire process is. In the last few years, research groups including teams at NASA's Goddard Space Flight Center have performed sophisticated numerical simulations of binary neutron star magnetospheres in the final stages of inspiral. These simulations solve the equations of relativistic electrodynamics on powerful supercomputers, tracking the evolution of the magnetic fields, the plasma, and the radiation as the two neutron stars orbit each other at relativistic speeds. The results are stunning. The simulations show exactly the process we've been describing. Magnetic field lines from the two stars connect across the gap. The orbital motion stretches and twists these connections. Current sheets form at boundaries between oppositely directed fields. Reconnection initiates in those current sheets, releasing bursts of energy. Particles are accelerated. Radiation is produced. Then the cycle repeats. But the simulations also reveal details that were not anticipated from simple theoretical arguments. The reconnection doesn't happen uniformly across the interaction region. It's highly localized, occurring in specific spots where the field geometry creates favorable conditions. These reconnection sites can move, appearing in different locations as the orbital geometry shifts. The result is that the electromagnetic output of the system is not steady. It flickers, producing rapid bursts and dips in luminosity that vary on timescales of milliseconds, or even shorter, tracking the frantic orbital motion of the neutron stars. And there's something else the simulations reveal that explains why this flickering is so intense. Something that solves a problem hiding in the description I gave earlier. Remember, I said that reconnection initiates at a tiny point where the frozen-in condition breaks down due to finite resistance. That's true. But if reconnection only happened at one tiny point, the rate of energy release would be far too slow to explain the explosive bursts the simulations show. A single reconnection point processing field lines one by one through a tiny diffusion region simply cannot convert magnetic energy into particle energy fast enough. It would be like trying to drain a lake through a drinking straw. The energy is there, but the bottleneck is too narrow. What actually happens is far more violent. When a current sheet forms between the merging neutron stars and reconnection begins, the current sheet doesn't stay intact. It becomes unstable. The thin layer of opposing fields, stretched and compressed by the orbital dynamics, develops a particular kind of instability that causes it to break apart. Instead of remaining a smooth, continuous sheet, it fragments into a chain of magnetic structures called plasmoids. Think of a plasmoid as a bubble of magnetic field. When the current sheet fragments, the field lines in the sheet reorganize into a series of closed loops, each one forming a self-contained magnetic island embedded in the sheet. Between each pair of adjacent plasmoids, a new, smaller reconnection site forms. So instead of one reconnection point processing field lines slowly, you suddenly have dozens or hundreds of reconnection points operating simultaneously, each one converting magnetic energy into particle energy independently. And then those plasmoids themselves begin to interact. Adjacent plasmoids can merge, colliding and combining into larger plasmoids. Each merger is itself a reconnection event, releasing additional energy, accelerating more particles, producing more radiation. The large plasmoids that form from these mergers can then merge with other large plasmoids, releasing even more energy. It's a cascade. The current sheet doesn't just reconnect, it shatters into a hierarchy of magnetic structures that interact, merge, and reconnect at every scale. From the largest plasmoids, spanning a significant fraction of the gap between the stars, down to the smallest structures at the limits of what the plasma physics can sustain. This is what makes reconnection fast enough to matter. Instead of one straw draining the lake, the dam breaks into 1,000 pieces, and the water rushes out through every gap simultaneously. The fragmentation of the current sheet into plasmoid chains accelerates the overall reconnection rate by orders of magnitude compared to what a single reconnection point could achieve. It transforms reconnection from a slow, steady process into an explosive, bursty one. And this fragmentation directly explains the flickering that the simulations predict. Each plasmoid merger produces its own localized burst of energy. Each burst has a characteristic timescale related to the size of the plasmoids involved. Large plasmoid mergers produce longer, more energetic bursts. Small plasmoid mergers produce shorter, fainter bursts. The superposition of all these bursts happening at different locations, at different times, at different scales, creates the complicated, rapidly varying electromagnetic output that the simulations show. The flickering isn't random noise. It has structure tied to the fragmentation and merging of magnetic islands in the current sheets between the stars. The simulations also show the formation of other complex structures in the magnetosphere. Twisted flux tubes, large-scale magnetic loops that can extend well beyond the immediate vicinity of the stars. These structures carry currents, trap plasma, and radiate. They form and dissolve on orbital timescales, creating a rapidly evolving electromagnetic environment that changes character with every revolution of the binary. One particularly important finding from these simulations concerns the total electromagnetic luminosity. The total power output in electromagnetic radiation from the pre-merger interaction. The simulations suggest that in the final few orbits before contact, the electromagnetic luminosity can reach values in the range of 10 to the 43rd to 10 to the 45th watts. For comparison, the total luminosity of the Sun is about 4 times 10 to the 26 watts. The pre-merger electromagnetic emission from the magnetospheric interaction can briefly exceed the Sun's luminosity by a factor of roughly a billion or more. And this is before the stars even collide. That number needs context. It's enormous by any normal standard. The entire energy output of our Sun, every photon of light and heat it produces each second, multiplied by over a billion, and that's what the magnetic interaction between two neutron stars can produce in the final moments before they touch. But by the standards of the merger itself, by the standards of what comes after, it's actually modest. The gravitational wave luminosity in the final moments exceeds the electromagnetic output by many orders of magnitude, and the post-merger gamma-ray burst and kilonova will dwarf the pre-merger electromagnetic emission. The precursor signal is a whisper compared to the scream that follows. But a whisper can still be heard if you know when and where to listen. And the precursor signal carries information that the post-merger signals do not. It tells you about the magnetic field strengths and orientations of the two neutron stars before they merged. It tells you about the plasma conditions in the interaction region. It tells you about the physics of reconnection in the most extreme electromagnetic environment imaginable. These are things you cannot learn from the gravitational waves alone, and you cannot learn them from the post-merger radiation. Because by then, the magnetospheric structure has been destroyed, replaced by the chaotic aftermath of the collision. The simulations also highlight something else that is critically important. The character of the pre-merger electromagnetic emission depends strongly on the magnetic field properties of the individual neutron stars. If both neutron stars have relatively modest magnetic fields in the range of 1 billion to 1 trillion Gauss, the pre-merger electromagnetic output is on the lower end of the predicted range. Detectable perhaps, but faint. But if even one of the neutron stars is a magnetar with a field of 1 quadrillion Gauss or higher, the pre-merger electromagnetic luminosity can be thousands or millions of times greater. A magnetar strength field means vastly more magnetic energy available for reconnection to release, vastly stronger electric fields for particle acceleration, vastly more intense radiation. The probability that any given binary neutron star merger involves a magnetar is uncertain. Magnetars are relatively rare among neutron stars. Most neutron stars have fields that are strong but far below magnetar levels, and magnetic fields decay over time. A neutron star that was born as a magnetar may have lost much of its extreme field strength over the millions of years it takes for the binary to spiral together. By the time the merger occurs, both neutron stars might have relatively ordinary fields, but some mergers might involve younger neutron stars with stronger residual fields. And even ordinary neutron star fields can produce detectable precursor emission if the conditions are right, and the detectors are sensitive enough. The simulations suggest a range of possibilities, from barely detectable to spectacularly bright, depending on the specific properties of the merging objects. Another important finding from the simulations is the role of the orbital separation in determining the reconnection rate. When the neutron stars are still widely separated, reconnection events are rare and weak. The field lines barely interact. But as the separation shrinks, and especially once the magnetospheres begin to significantly overlap, the reconnection rate climbs steeply. In the very final orbits, when the stars are separated by just a few stellar radii, the entire interaction region is in a state of continuous, violent reconnection. Field lines are connecting, stressing, breaking, and reconnecting dozens or hundreds of times per second. The electromagnetic output reaches its peak in these last few orbits, right before the surfaces make contact. This has an important observational consequence. The precursor emission, if it exists, should be concentrated in a very narrow time window. Most of the electromagnetic energy from the magnetospheric interaction is released in the final few seconds before merger. A detector looking for this signal needs to be watching at exactly the right time and looking in exactly the right place. Given how brief and how localized the signal is, catching it requires either incredible luck or advance warning. And as we'll discuss later, gravitational wave detectors can provide exactly that advance warning. There's one more aspect of the reconnection physics that deserves attention before we move on. Magnetic reconnection doesn't just accelerate particles and produce radiation, it also generates waves. When field lines snap and reconfigure, the sudden change in the magnetic field creates disturbances that propagate outward through the magnetized plasma. These are called magnetohydrodynamic waves, or more simply, magnetic waves. They carry energy outward from the reconnection site, depositing it in surrounding plasma, heating it, stirring it, creating turbulence. In the final stages of inspiral, these waves fill the entire interaction region. The space between the neutron stars becomes turbulent on every scale, from the larger structures spanning the gap between the stars down to the smallest dissipative scales where energy is finally converted into heat and radiation. This turbulence adds another layer of complexity to the electromagnetic output. It makes the signal variable and unpredictable, with bursts and fluctuations on every time scale from seconds down to microseconds. The full picture then is this: two neutron stars spiraling toward each other at an ever-increasing rate. Their magnetospheres overlapping, field lines connecting, being stretched and twisted by the orbital motion. Current sheets forming where oppositely directed fields meet. Those current sheets fragmenting into chains of plasmoids that merge and reconnect at every scale, releasing energy explosively. Particles accelerated to extreme velocities. Synchrotron and curvature radiation produced across a wide spectrum. The highest energy photons partially absorbed through pair production, reprocessing the radiation to lower energies. Magnetic waves and turbulence filling the interaction region. Enormous electrical currents flowing through the plasma along connected field lines. and all of it escalating, growing more intense, more frequent, more violent, as the orbital separation shrinks and the moment of contact approaches. This is not a gentle process. This is not a quiet prelude. The magnetic interaction between merging neutron stars, in the minutes and seconds before they touch, is one of the most extreme electromagnetic events the universe produces. It involves energy scales that dwarf anything in our solar system. It involves particle energies that rival the most powerful accelerators ever conceived. It involves magnetic field dynamics so complex that only the most advanced supercomputer simulations can even begin to capture them. And yet, from our perspective here on Earth, tens or hundreds of millions of light years away, this entire cataclysm is playing out in an object smaller than a city. Two 12-mile spheres separated by a gap of a few miles, screaming around each other hundreds of times per second, their magnetic fields tearing at the fabric of space between them. The entire battlefield, the entire arena where this electromagnetic war is being fought, would fit comfortably inside a single county on Earth. And the war itself, from the first significant magnetic contact to the final moment of stellar collision, lasts only minutes. Everything we've described so far, the field connections, the stress accumulation, the reconnection, the plasmoid cascades, the particle acceleration, the radiation, the pair production, all of it is the system's attempt to release the magnetic energy that the orbital dynamics keep pumping in. But the orbital inspiral is relentless. Gravity always wins. The stars keep spiraling closer. The magnetic stress keeps building faster than reconnection can dissipate it. The system is overwhelmed. And that's what makes the final second so extraordinary. The reconnection rate reaches its peak, but it's still not fast enough to drain the magnetic energy as fast as the orbital motion is injecting it. The magnetic field in the interaction region reaches extreme intensities. The currents flowing through the plasma become enormous. The particle acceleration reaches its maximum efficiency. The electromagnetic luminosity climbs to its highest value. And then the neutron star surfaces finally meet. But we're not quite there yet. Because before we reach that final moment, there's one more critical question to address. Can we actually see any of this? Can the electromagnetic signals produced by this pre-merger magnetic battle actually reach us? And if they can, how do we distinguish them from everything else that's happening? The gravitational waves, the post-merger gamma ray burst, the kilonova that follows days later. What does a pre-merger electromagnetic signal look like? And how close are we to actually detecting one? So let's talk about detection. Because everything we've described so far, the magnetic field connections, the reconnection, the particle acceleration, the bursts of high-energy radiation, all of it is a prediction. It comes from theory and from simulations. The question that matters most to astronomers right now is whether any of this pre-merger electromagnetic activity can actually be observed. And to answer that question, we need to understand what other signals a neutron star merger produces, because the precursor emission doesn't arrive in isolation. It arrives as part of a sequence. And distinguishing it from everything else in that sequence is one of the great observational challenges in modern astrophysics. A neutron star merger produces three main categories of signal, and they arrive at different times, carry different information, and are generated by completely different physical processes. Understanding all three is essential for recognizing what makes the pre-merger electromagnetic signal unique. The first signal is gravitational waves. These arrive throughout the inspiral, growing stronger and higher in frequency as the neutron stars spiral closer. Gravitational wave detectors like LIGO and Virgo observe the inspiral as a chirp, a signal that sweeps upward in both pitch and loudness over the final minutes and seconds before merger. The gravitational wave signal encodes information about the masses of the two neutron stars, their orbital parameters, and the dynamics of the inspiral. It tells you when the merger is about to happen and roughly where in the sky it's occurring. Gravitational waves pass through matter without being absorbed or scattered. They travel at the speed of light and arrive at Earth carrying a pristine record of the orbital dynamics. The second signal is a short gamma-ray burst. This arrives after the neutron stars have already made contact. When the two stars collide, the merger remnant, either a hypermassive neutron star that survives briefly, or a black hole that forms almost immediately, can launch a pair of ultra-relativistic jets along the axis perpendicular to the original orbital plane. These jets plow through the surrounding debris at nearly the speed of light, producing intense gamma-ray radiation through internal shocks and other processes. The gamma-ray burst is incredibly bright but very brief, lasting typically less than 2 seconds, and it is beamed. The radiation is concentrated into narrow cones along the jet axis. If Earth doesn't happen to lie within or near one of those cones, the gamma-ray burst is either invisible or dramatically fainter. The third signal is the kilonova. During the merger, enormous quantities of neutron-rich matter are flung outward from the collision site. This material is so neutron-rich that it undergoes rapid neutron capture, a nuclear process called the R process, building up heavy elements far beyond iron on the periodic table. Gold, platinum, uranium, and dozens of other heavy elements are forged in these ejected clouds of matter. These freshly created heavy elements are radioactive. As they decay, they release energy that heats the expanding cloud of debris, causing it to glow. This glow is the kilonova. It peaks days after the merger, fading over the following weeks. The kilonova radiates across a broad range of wavelengths, from ultraviolet through visible light to infrared, and it is roughly isotropic, meaning it can be seen from any direction, unlike the beamed gamma-ray burst. Now, where does the pre-merger electromagnetic signal fit into this sequence? It sits right at the beginning, before the gamma-ray burst, before the kilonova, overlapping with the final stages of the gravitational wave chirp. The pre-merger signal is produced by the magnetospheric interaction we've been describing. The field connections, the reconnection, the particle acceleration, all happening in the final minutes and seconds before the stellar surfaces touch. It should arrive at Earth at essentially the same time as the last portion of the gravitational wave signal, or perhaps very slightly before the gravitational wave signal reaches its peak, because the electromagnetic interaction begins while the stars are still separated. This timing is what makes the pre-merger signal scientifically precious. The gravitational waves tell you about gravity, about masses and orbits. The gamma-ray burst tells you about the post-merger jet. The kilonova tells you about the ejected matter and nuclear physics. But the pre-merger electromagnetic signal tells you about the magnetic fields of the neutron stars themselves, measured in the final moments before they were destroyed. It tells you about the strength of those fields, their orientation, their interaction. It reveals the electromagnetic environment of the merger in real time, as it's happening. No other signal provides this information. Once the stars collide, the magnetospheric structure is annihilated. The organized field configurations, the current sheets, the reconnection sites, all of it is destroyed in the violence of the impact. The gamma ray burst jet forms from a completely different process, driven by the accretion of matter onto the merger remnant, not by the pre-merger magnetospheric interaction. And the kilonova is driven by radioactive decay in ejected matter, having nothing to do with the original magnetic fields at all. So the pre-merger electromagnetic signal is irreplaceable. It carries information that is available at no other time and from no other source. But it also poses enormous observational challenges. The signal is expected to be brief, lasting at most a few seconds at detectable intensity. It is expected to be faint compared to the gamma ray burst and the kilonova that follow. And it arrives during or just before the moment when every telescope in the world is about to be overwhelmed by the much brighter post-merger signals. Let's talk about the one event that reshaped everything we know about neutron star mergers. Because in 2017, astronomers witnessed something that had never been seen before, and it set the stage for the search for pre-merger signals that continues today. On August 17th, 2017, at 12:41 Universal Time, the LIGO detector in Hanford, Washington, and the LIGO detector in Livingston, Louisiana, simultaneously recorded a gravitational wave signal. It was designated GW170817. Milliseconds later, the Virgo detector in Italy registered the same signal, though far more faintly, because the source lay in a direction where Virgo had reduced sensitivity. This wasn't the sharp, brief chirp of merging black holes that LIGO had detected before. This was different. The signal lasted about 100 seconds in the detectable frequency band, sweeping slowly upward in pitch and intensity. It was the unmistakable signature of two neutron stars spiraling toward each other. The gravitational wave chirp stretching out over nearly 2 minutes as the stars completed their final thousands of orbits. The source was located approximately 130 million light-years away. That's relatively close by cosmological standards, close enough that astronomers immediately knew this event would be extraordinary. For the first time, they had a gravitational wave advance warning of a neutron star merger, and they had the sky localization to go looking for the electromagnetic counterpart. What happened next was one of the most remarkable mobilizations in the history of science. Within minutes of the gravitational wave detection, automated alerts went out to observatories around the world. Approximately 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope and the Integral satellite detected a short gamma ray burst, designated GRB170817A. The gamma ray burst was faint by the standards of typical short gamma ray bursts, but it was real and it was clearly associated with the gravitational wave event. The slight delay of 1.7 seconds between the end of the gravitational wave signal and the arrival of the gamma rays was consistent with the time needed for the merger remnants to launch a jet and for that jet to produce gamma rays through internal shocks. Then, the ground-based hunt began. Astronomers on every continent pointed telescopes at the patch of sky where the gravitational waves had originated. Within 11 hours, a team using the SWOPE telescope in Chile found it. A new point of light in the galaxy NGC 4993, a galaxy that hadn't shown anything unusual before. It was the kilonova, designated AT 2017 GFO, the optical glow of freshly forged heavy elements expanding outward from the collision site. Over the following days and weeks, more than 70 observatories on 7 continents and in space observed the event across the entire electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays, and gamma rays. The kilonova appeared initially blue and bright, then faded and reddened over the following days as the expanding cloud of debris cooled and heavier. More opaque elements dominated the emission. The spectral signatures of heavy elements like strontium were identified in the kilonova light, providing the first direct observational confirmation that neutron star mergers produce heavy elements through the R process. These collisions are indeed cosmic forges where the heaviest elements in the periodic table are created. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. Elements like these were born in events like this one, scattered into space by ancient neutron star mergers, eventually incorporated into the gas clouds that formed our solar system billions of years later. GW1708-17 was a landmark event. It inaugurated the era of multi-messenger astronomy with neutron stars, confirming decades of theoretical predictions about mergers, gamma-ray bursts, and kilonovae all in a single observation. Thousands of scientists contributed to the analysis. The results were published simultaneously in dozens of papers. It was, by many measures, the most thoroughly observed astronomical event in human history. But for our story, the most important question is what it revealed about pre-merger electromagnetic emission. The answer, to be direct, is not much. No convincing pre-merger electromagnetic signal was detected from GW1708-17. The gamma-ray burst arrived after the merger, consistent with being a post-merger jet phenomenon. The kilonova appeared hours later. Nothing was clearly identified as electromagnetic emission from the magnetospheric interaction before the stars touched. But this doesn't mean the pre-merger signal wasn't there. There are several important reasons why it might have been present but undetected. First, the magnetic field strengths of the 2 neutron stars in this particular merger are unknown. If both stars had relatively modest magnetic fields, in the range of 1 billion Gauss or below, as is typical for old neutron stars that have been in a binary for millions of years, then the predicted pre-merger electromagnetic luminosity would have been at the low end of the range from simulations. It might have been too faint to detect at a distance of 130 million light years with the instruments that were available. Second, the time window for observing the precursor was extremely short. The gravitational wave signal from the merger lasted about 100 seconds in the sensitive frequency band of the LIGO detectors. The final few seconds, when the pre-merger electromagnetic emission would have been strongest, represent a tiny fraction of that already brief period. Gamma-ray telescopes were observing the sky, but their sensitivity to a brief, faint signal arriving from a specific direction during a specific fraction of a second is limited. Third, the orientation of the system matters. The pre-merger electromagnetic emission may be anisotropic, meaning it might be stronger in some directions than others, depending on the magnetic field geometry and the orbital plane orientation. If Earth was not favorably positioned to receive the strongest emission, the signal would have been weaker than the most optimistic predictions. So, the non-detection of a pre-merger signal from GW1708-17 is not evidence that pre-merger signals don't exist. It's consistent with the signal being present, but below the detection threshold of existing instruments for this particular event. The simulations predict a wide range of possible luminosities, and the low end of that range is genuinely difficult to detect with current technology. This is an important distinction. Simulations predict that pre-merger electromagnetic emission should occur. The physics demands it. When two magnetized spinning neutron stars approach each other, their magnetospheres interact, reconnection occurs, particles are accelerated, and radiation is produced. This is not speculative. It follows directly from well-established laws of electrodynamics applied to the known properties of neutron stars. The question is not whether the emission exists. The question is whether it's bright enough and whether our instruments are sensitive enough to catch it. And this is where the next generation of detectors becomes critically important, because the search for pre-merger electromagnetic signals is fundamentally a multi-messenger problem. You need gravitational wave detectors to tell you when a merger is happening and roughly where to look. And you need electromagnetic telescopes, fast ones, sensitive ones, covering a wide range of wavelengths, to catch the faint, brief precursor signal in the right patch of sky at the right moment. Current gravitational wave detectors, LIGO and Virgo, detect neutron star mergers out to a few 100 million light-years. They provide advance warning of a few tens of seconds to a few minutes before the merger occurs, depending on when the signal enters their sensitive frequency band. The sky localization is rough, often tens of square degrees, which means electromagnetic telescopes have to search a large area of sky very quickly to find the counterpart. Next generation gravitational wave detectors, currently in planning and development, will transform this picture. The Einstein telescope, a proposed European underground detector, and Cosmic Explorer, a proposed American detector with arms 10 times longer than LIGO's, would be sensitive enough to detect neutron star mergers across the entire observable universe. But more importantly for our story, they would detect the inspiral signal much earlier. Instead of picking up the signal tens of seconds before merger, these detectors could pick it up minutes or even hours before the stars touch. This dramatically extends the advance warning time, giving electromagnetic telescopes far more time to slew into position and begin observing the right region of sky before the precursor emission reaches its peak. This early warning capability is transformative. Imagine knowing that a neutron star merger is going to happen in a specific part of the sky in exactly 4 minutes. You could point X-ray telescopes, gamma-ray monitors, radio arrays, and optical telescopes at that patch of sky and watch. You could be staring directly at the system when the pre-merger electromagnetic emission reaches its maximum intensity in the final seconds before contact. Instead of discovering the emission after the fact, buried in archival data, you could observe it in real time. On the electromagnetic side, new and planned facilities also improve the prospects. Wide-field X-ray monitors with better sensitivity and faster response times could catch brief precursor flashes that current instruments would miss. Next-generation radio arrays could detect coherent radio emission from the magnetospheric interaction, signals that might be produced by mechanisms similar to those that generate pulsar radio emission, but amplified by the extreme conditions of the pre-merger environment. Rapid response optical and infrared telescopes could search for any lower energy counterparts. The combination of next-generation gravitational wave detectors providing early, precise warnings and next-generation electromagnetic telescopes providing the sensitivity and response speed to act on those warnings creates a realistic path toward detecting pre-merger electromagnetic signals for the first time. Most researchers in the field believe this is not a question of whether it will happen, but when. The physics says the signal should be there. The instruments are being built to find it, and finding it would be scientifically profound in ways that go far beyond simply checking a box on a list of predictions. Consider what a confirmed detection would actually reveal. The brightness and spectrum of the pre-merger signal would directly constrain the magnetic field strengths of the two neutron stars just before merger. This matters because the magnetic field of a neutron star is connected to its internal structure. The field is generated and sustained by currents flowing in the superconducting interior of the star, where neutrons form a superfluid and protons form a superconductor. How those internal currents evolve over millions of years, how the field decays or is maintained, depends on physics that we cannot probe any other way. The interior of a neutron star is the densest material in the known universe, and the behavior of matter at those densities is one of the great unsolved problems in physics. A measurement of the magnetic field just before merger would provide a data point that theorists could use to constrain models of neutron star interiors, telling us something about the behavior of matter at densities that no laboratory on Earth can reproduce. The variability of the pre-merger signal, how it flickers and fluctuates on millisecond timescales, would tell us about the dynamics of magnetic reconnection in relativistic pair plasma. Reconnection is a universal process. It happens on the Sun, in Earth's magnetosphere, in laboratory plasmas, and in astrophysical jets. But it has never been observed in a regime where the magnetic energy density exceeds the rest mass energy density of the plasma by orders of magnitude. That regime exists between merging neutron stars and nowhere else that we can currently observe. Detecting the pre-merger signal would give us the first observational window into the most extreme reconnection physics the universe produces. And the polarization of the signal, if measurable, could reveal the geometry of the magnetic field in the interaction region, telling us about the relative orientation of the two neutron stars' magnetic poles, and providing constraints on the configuration of the magnetosphere at the moment of its destruction. All of this information vanishes the instant the stars collide. It exists only in the pre-merger window. Miss it, and it's gone. Catch it, and you've opened a window onto physics that is available at no other time and from no other source. Now, let's go to the end. Let's talk about the final seconds. The neutron stars are now separated by a distance comparable to their own diameters. 20 kilometers, 15, 10. They're orbiting each other many hundreds of times per second. Their surfaces are almost touching. The gravitational wave signal has swept up to frequencies above 1,000 Hz, screaming at the upper edge of detector sensitivity. The gravitational wave luminosity in these final instants exceeds the total light output of every star in our galaxy 10 billion times over. More energy is being radiated in gravitational waves during these last few seconds than the Sun will produce in its entire 10 billion year lifetime. And the magnetic interaction has reached its absolute peak. The magnetospheres are no longer two separate structures. They are completely entangled, merged into a single, chaotic, rapidly evolving electromagnetic environment that envelops both stars. Current sheets are everywhere. Reconnection is happening continuously at hundreds of sites simultaneously, driven by the impossibly fast orbital motion. The magnetic field in the interaction region has been amplified by compression and by the winding of field lines to values that may approach or even exceed magnetar strength. regardless of what the original field strengths of the individual stars were. Enormous electrical currents thread through the plasma, connecting the two stellar surfaces through bridges of relativistic particles. Particles are being accelerated to the highest energies the system will ever produce. Synchrotron and curvature radiation flood the interaction region with high-energy photons. Pair production cascades fill the space with newly created electrons and positrons. Magnetic waves and turbulence churn through the plasma on every scale. The electromagnetic luminosity reaches its maximum, a brief, intense peak that dwarfs anything the magnetospheric interaction produced in the preceding minutes. The tidal forces are now so extreme that the neutron stars themselves are visibly deformed. Their surfaces bulge toward each other, pulled into elongated shapes by the tidal gravity of their companion. The crystalline crust, harder than any material on Earth by factors of billions, begins to crack and shift under the strain. The magnetic field footprints on the surface, anchored to the crust, are dragged and distorted as the crust deforms. The external field geometry changes rapidly, adding yet more variability to the already chaotic electromagnetic environment. The separation drops below the sum of the two stellar radii. The outer layers of the two neutron stars begin to make physical contact. Matter from one star touches matter from the other for the first time. This is not a gentle meeting. The material at the contact point is moving at a significant fraction of the speed of light. The collision drives a shockwave into the stellar material, heating it to temperatures of tens of billions of degrees. Nuclear reactions ignite at the interface, transforming the composition of the matter. Neutron-rich material is squeezed, heated, and flung outward by the violence of the impact. At this precise moment, the story we've been telling ends. The pre-merger magnetic interaction is over. The magnetospheres, those intricate structures of organized field lines and trapped plasma that we spent so long describing, are destroyed. They're overwhelmed by the catastrophic violence of the collision. The organized field configurations are shredded, replaced by turbulent, chaotic magnetic fields generated by the collision itself. The current sheets, the reconnection sites, the particle acceleration regions, all of it is swept away in the cataclysm. What comes next is a different story. The merger remnant forms either a massive neutron star that survives for milliseconds or seconds before collapsing into a black hole, or a black hole that forms almost immediately. Matter falls onto this remnant, forming an accretion disk. Jets may be launched along the polar axis, producing the gamma ray burst. Neutron-rich matter ejected during the collision expands outward, undergoing R-process nucleosynthesis, creating heavy elements, and eventually producing the kilonova glow days later. These post-merger processes are extraordinary in their own right, and they have been the subject of intense study for decades. But the pre-merger electromagnetic interaction, the battle between the magnetospheres, is something different. It's a story that takes place in the brief window between when the magnetic fields first begin to interact and when the stars finally collide. A window measured in minutes at most. A window during which two of the most powerful magnetic structures in the universe overlap, connect, stress, break, and reconnect, producing electromagnetic fireworks on a scale that is difficult to fully comprehend. This is a story that, as of today, remains largely in the realm of theoretical prediction and numerical simulation. No pre-merger electromagnetic signal has been definitively, routinely detected from a neutron star merger. The physics tells us these signals should exist. The simulations tell us roughly how bright they should be and what they should look like. But observational confirmation is still ahead of us, waiting for the right combination of a nearby merger, favorable geometry, and sensitive instruments all aligned at the right moment. When that detection finally comes, and most researchers believe it will come within the next decade or two as next-generation detectors come online, it will open an entirely new window on the universe. It will reveal the electromagnetic fingerprint of the final moments before one of the most violent events in the cosmos. It will tell us about magnetic fields, about plasma physics, about particle acceleration, about reconnection, all under conditions so extreme that no experiment on Earth could ever reproduce them. And it will complete the multi-messenger picture of neutron star mergers, adding the one missing piece, the electromagnetic prelude, to a story that currently begins with gravitational waves and ends with the fading glow of a kilonova. There is something worth reflecting on as we reach the end of this story. Everything we've described tonight, every process, every mechanism, every burst of energy and cascade of particles takes place in an arena smaller than a city. Two objects 12 miles across, separated by a gap of a few miles, with the entire electromagnetic battle fought in a volume that would fit inside a single county. And the whole thing, from the first meaningful magnetic contact to the moment of collision, lasts only minutes. Minutes. After millions of years of slow, patient inspiral, after billions of years since the original stars were born, lived their lives and died in supernova explosions. After the extraordinary improbability of both stars collapsing into neutron stars, of the binary surviving two supernova kicks, of gravitational wave emission grinding the orbit down over geological epochs. After all of that, the magnetic story we've been telling plays out in less time than it takes to brew a cup of coffee. And yet, in those few minutes, the universe produces an electromagnetic environment more extreme than almost anything else it creates. Magnetic fields amplified beyond magnetostrength. Particles accelerated to energies that rival the output of the most powerful machines humans have ever built. Reconnection operating in a regime so extreme that theory alone cannot fully describe it, and only the most advanced simulations can approximate it. Energy releases that briefly outshine everything in our solar system combined, radiated from a space smaller than a neighborhood. We are living in the first era of human history where detecting this story is even conceivable. A century ago, we didn't know neutron stars existed. Half a century ago, we hadn't confirmed gravitational waves. A decade ago, we hadn't seen a neutron star merger in both gravitational waves and light simultaneously. The instruments that could catch the pre-merger electromagnetic signal, the whisper before the scream, are being designed and built right now. The physicists and engineers working on the next generation of gravitational wave detectors and electromagnetic observatories are building the ears that will hear this whisper for the first time. So, the next time someone tells you that the story of a neutron star merger starts when the stars collide, you'll know better. The story starts earlier. It starts when two magnetic fortresses, built by the collapsed cores of dead stars, spinning and radiating and crackling with electromagnetic energy, begin to reach across the shrinking space between them. It starts when field lines connect, when currents flow, when reconnection fires, when particles scream outward at nearly the speed of light and photons blaze through magnetized plasma so intense It can turn pure light into matter. The collision is the ending. The magnetic fields touching is where the story truly begins. And that story, written in the language of electromagnetic radiation and gravitational waves, is one that the universe has been telling for billions of years, in events scattered across every galaxy, in mergers that have already happened countless times before anyone was around to witness them. We are only now building the instruments sensitive enough to hear it. And when we finally do, when the first confirmed pre-merger electromagnetic signal arrives at a detector on or near Earth, we will have captured something extraordinary. Not just a signal, but a message from the final seconds of two dead stars, written in light and magnetism, telling us about the most extreme physics the universe knows how to produce. A message that travelled across millions of light years, carrying information that existed for only a few fleeting moments before being destroyed forever in the violence of the collision. That message is out there, right now, travelling through space from mergers we haven't detected yet. It's encoded in photons launched by reconnection events between magnetospheres we've never observed. And somewhere, in a future that might be only years or decades away, we will catch it. We will decode it. And we will understand, for the first time, what really happens when two neutron stars' magnetic fields touch.